has the pixel buffer, Z buffer, size of the screen and everything.
Mm-hmm.
And basically the way I have it is that the screen just kind of has those buffers, and that's really it. It doesn't else. And then for the triangle has a rasterized function that takes in a screen as a parameter to rasterize to.
Mm-hmm.
And I just made that default standard screen.
Yeah, you call it a screen buffer, sure. Yeah, so your question was, do you have the screen render the triangles or the triangles render to the screen, right?
Yes.
So, great question. The difference there is whether or not you're doing ray tracing or traditional rasterization, right? So if you're doing ray tracing, then the screen, you loop over every pixel in the screen, and that pixel goes until it collides with geometry. And you've got some sort of data structure that will tell you the first bit of geometry you hit. The hardware acceleration uses what's called BVH, hierarchical bounding volumes. And so it's a very fast test to see what you hit with a ray. And then it gets complicated because once you hit something, you need to see if it's lit. And you need to see if it's transparent, then some of the light will reflect, some will go inside, and it'll have to refract. And so typically, every time a ray hits something, it scatters multiple rays, and it keeps going until it hits sort of a limit on how many rays come out of it. And also, a lot of times, to avoid aliasing effects, you'll supersample. So you'll send multiple rays kind of randomly within the pixel. Because, like, what if the geometry kind of cuts through half of the pixel, right? Some of the rays will bypass, some will hit it and reflect off. And so, if you, like your code, you have all the jaggies, and, it's normal. So you send multiple rays per pixel, and then the screen is handling the rendering, right? For every pixel on the screen, you send out rays and see what geometry they hit. You've got some big data structure holding the world geometry. See what happens, and then you can control the quality settings, right? Like when you play a game that has RTX enabled on it, there's a quality setting that basically controls how many rays go out, right? And so the more rays you send out and the more rays that reflect, the better the quality you get, but the slower the processing is going to be. The other way around is you have your rasterization pipeline, and right now, it's not much of a pipeline, right? I don't think you're doing any of the normal stuff that we would do, which is like, is this thing visible, right? The first thing you have to do is you have to translate it from world coordinates into screen coordinates, right? And if the thing is off the screen, you just don't render it. And then you do the backface culling if the hole goes the opposite way, which you can figure out just by cross-producting the two basis vectors of a triangle. You can tell if it's facing forwards or backwards based on if it's positive or negative. So quick cross-product, which graphics cards are very fast at. Okay, this thing's backwards, don't draw it. And then you do a near clipping plane, it's too close. Far clipping plane, it's too far. And then, if you've got a data structure that holds like your potentially visible set, then you don't go over every triangle in the world. You grab the potentially visible set, you grab that list of triangles, and then try rasterizing those. And so, but at the end of the day, we're doing what you have here, which is for every triangle, block, figure out its bounding box, go over every pixel if it's within the triangle, write it to the screen buffer, write it to the Z buffer, and the other buffers as well, right? There's like motion blur buffers and
so for the rasterization, when we do actually do real projection rasterization, that's kind of what we're gonna have to do, like you said, with the backface culling and all that.
You don't have to. I mean, in OpenGL, you can turn on double-sided triangles. Like it's fine. It's just normally in a video game you want speed, and it's very rare that you need to see the backside of a triangle. It usually only happens when your near clipping plane clips into something. Like if there's a branch of a tree and your camera moves around the branch of the tree and the near clipping plane takes off the front geometry of it, now you're looking inside of the branch all those.
And just seeing the world.
Yeah, and you can
see the skybox.
Yeah,
I've seen that before.
Yeah. And so sometimes you'll turn on double, and you can turn it on and off, right? And so basically, it's just a setting. You're like turn on double-sided triangles while drawing the tree because I'm close to it, And then for everything else, you turn off double-sided triangles, And you can do that so you don't get these weird bugs where the camera goes inside of, a branch and then you can see through it and stuff like that. So you don't have to do that. But yeah, the next step is going to be projecting from world coordinates into screen space coordinates, and it's not too bad. You typically have a matrix set up for the view and for the camera. And so as the camera moves around, like if you slide the camera 5 to the right, then all the objects on the screen will slide to the left, right? Right. And so that's just a matrix transform. Probably for your math thing here, you're gonna need matrix math stuff. Translate, rotate, scale, matrix multiplies, vector times matrix, scalar times matrix, matrix times matrix, and what's up, bro? It's a roll of toilet. No, it's paper towel. What's up? Is that your thing?
I made something cool.
You made something cool? What is it?
If you hold it up to light, it can create rainbows.
I see.
No, like natural sunlight.
Yeah. Oh, look out the window.
No, a lot of natural sunlight.
Okay, you made a kaleidoscope. That's cool.
No, not exactly.
Yeah.
It just makes rainbows. Rainbow colors.
Very cool, bro.
So
get that after class.
I'm going to work on it.
Okay, so right, and so let's talk about projecting and things like that.
Do you want me to tell this my stream?
What was there any other thing that you wanted to know about
that? I mean, if we're gonna go over like pretty much after just going like in terms of the inheritance stuff like that, everything you showed me pretty good.
Yeah, and we weren't recording for that, so you want to pull that up real fast, just so that the people at home can see what we did earlier without needing to walk through all the steps on it. We can just pretend to be geniuses that got it right the first time.
Oh. Batman. Oh my god.
Okay. So we did separate compilation with templates, which is normally kind of impossible, but at the very bottom of a .cc file that you're doing template code in, you can put template class, name of the class, and then in angle brackets specify the types you want it to work with, and then C++ will generate code for it. Normally you cannot do separate compilation with templates because it doesn't know, you can't generate object code because you don't know what type it's going to have, right? It's a blank. T is a blank. And so with this, it'll copy and paste the vec3 class, fill in int for t, fill in double for t, fill in float for t, and you'll have 3 versions of the vec3 class, and those are the only 3 types it'll work for. But it's still better than that, than doing what you had before, which was copy pasted, int version, float version, whatever. Okay, let's look at the header file. All right, and so the header file is pretty straightforward. So you got a vector3 class. It's got an x, y, and a z. It's got comparison operator, not equal, plus, minus, times, divide, get magnitude squared, normalized. Okay. Edges is a pair of vector 3s, and a triangle is 3 vector 3s, right? Or is it 3 edges?
Actually, kind of both. Okay. I store both a vector of edges and a vector of vectors.
Interesting.
Depending on what I need to do the math. A lot of this can be optimized away, but I was in the process of doing that.
Yeah, that's fair. The cross product, does it take 3 points or does it take 2 edges?
Cross product just takes vectors.
3 of them, right?
Yeah. No, 2 of them. So what you do is whenever I do a cross product, I create one vector from two vectors. So I basically zero them.
You have the origin be the third point, right?
Yeah, so I make the begin part of the edge be like the 0. Mm-hmm. So I just subtract begin from both the end and the center. Mm-hmm. And this is how I do the checking if it's counterclockwise.
And so you have a scalar cross product and a vector cross product?
Yeah, so I have a cross product 2D, which is the scalar, and 3, which is returns a vector.
Cool. All right. You've got an inside check for triangle?
Yeah, so that happens in the rasterization.
You don't have a separate function for it. It's probably a good idea to tell if a point is within a triangle.
Yeah, I mean, it's just, so I just go for each of the edges, I cross product it exactly how you saw it, and then if it's less than 0, then it's not in the triangle, because I'm doing counterclockwise.
And then, are you using the barycentric coordinate system? I think you said you're doing. Are you? Okay.
So, oh wait, when you say barycentric, you mean for the
interpolation?
For the colors, right?
For the interpolation.
Interpolation of depth or interpolation of color?
Whichever.
So for interpolation of depth, I kind of did my own thing. I did. I basically treated the triangle like it was a plane. Mm-hmm. And then I basically solved for a plane equation. So basically you have the ax plus bx plus cx plus d equals 0. So I just I solved for d, and then in the constructor, and then I and then obviously the a, b, and c are just the normal vector for the plane. So that's why I calculate the normal vector right up here.
3D cross product. Yeah. Okay. Mm-hmm.
Yeah, so then we know ax, bx, cx, or we know ax, bx, or that's not, but we know everything except for z by the time we get here. So given an x and a y, we can find what the z coordinate should be on plane, which the plane is basically just a triangle. Mm-hmm. So I use that to solve for the z coordinate, and then it just checks. So I have a invalid default z buffer value, so just check if nothing's ever been written there.
Then it goes in.
So if nothing's ever been written there, then this could have been an or. So if nothing's ever written there, or the z coordinate that we just calculated is closer than the one that's already there, then we're gonna do all of the color checking stuff, and then else we're just gonna move on. That shouldn't be drawn to the screen. Okay. And then I do the barycentric coordinates for the color depth. So
So you're getting the area of the triangle using the cross product again, right?
Yeah, so I cross product 2D with each edge. So I have a red edge, a blue edge, and a green edge. Mm-hmm. That's what that enum's for. So I cross product with the red edge, cross product with the blue edge, cross product with the green edge, divide each by 2 because it's a triangle. And then I just use this little formula. So the red area, it's basically the percentage of the red area versus the total area, and then multiply it by 255 to get the value.
Yeah, or you could divide the area by 2, and then you don't have to divide those 3 things by 2. Algebra.
Oh, well, yeah. So,
yeah, or the other way around.
Oh no, because no, I'd still have to divide this by 2 because this cross product is going to be treated like it's a parallelogram regardless.
Yeah, but the thing is, you treat everything like a parallelogram, then they divide out.
Oh, yeah.
5 divided by 10 is the same as 1 divided by 2. You know what I mean?
Right. That's. And then
division by 2 is cheap, so it doesn't really matter.
And then I just write it to the screen buffer. Pretty much it.
Yeah, the red, the green, the blue. Yeah, okay. So it doesn't work. Your code doesn't work with arbitrary colors. It only works with the hard-coded red, green, and blue.
I don't know what you mean by that. Like
the user can't set a different color for each of the points.
Oh no! I mean, that wasn't part of it. Yeah. I mean, this is just I literally just wrote this as put a comment or something. Fancy coloring. Like, this isn't something you'd actually use in a rendering engine. It's just a way that we use to determine where the triangles end and start.
Okay, so let's let's talk about the next steps on this then. All right, let me switch over to my screen then.
This is what happens when you don't fix the.
Yeah. No, it's a good idea to bake the reset in or something. I don't know.
It's all in H file, shouldn't be bad.
I mean, if other people are using it, they might not like me sticking things.
But like, it's either that or their terminal breaks. Like,
but I mean, I don't know. I don't know if I like registering things in their add exit, for them.
I guess.
Maybe just have a function that we recommend called.
Yeah. You could do like a
register
cleanup function or something.
Yeah, prepare for destiny.
Don't touch my stuff.
Prepare to meet your maker. All right. Okay, so good job on that. Let's talk next step for next week. It's kind of a pinkish color. Okay. So we've got a triangle right now, right? So there's right now it's.
Oh, you're not streaming, by the way.
I'm not. Shoot. Screen to stream. Me? Wait, what? Here? Is it streaming?
Yeah, we see it.
Why do I have this giant thing up here? Can I close this? Am I still streaming? Hello?
Yep.
Okay.
Yeah,
cool.
We see.
Don't touch my stuff. Okay. So, next steps are going to be projection. So if you have a screen like this, you've got a camera with a field of view. That's one too many lines. Whatever. And so you can have a triangle out there in world space, right? So this is going to be like 3, 4, 5 in world space and whatever. And maybe you can make it rotate. Wouldn't that be cool? Have the thing rotating like when you boot up like a PlayStation 1 or something, it does like some really cheesy 3D artwork or something like that. That'd be kind of fun. So you need to project these things to pixels on the screen, right? And I have a link for you on that. Right here. And for that, you will need to have your matrix math thing working too. So a matrix times scalar, matrix times vector, matrix times matrix. And so remember, there's three types of spatial coordinates, right? If you got an airplane here, you got what's called local space. This website calls it model space for some reason. Okay, I call it local space. And so this guy is going to have like an X, a Y, and a Z there. But in the world, the world, and this is the origin for the model. And in the world, maybe the X is this way and the Y is this way, and the Z is this way. Like it. And so to project from one space into the other, what you do, it's a matrix operation, and that website runs through the details on it. But basically, if this was 0, 0, 0 before, now when you project, when you translate from local space to world space, it's now at 300, 4,000, -50 or something like that. So that's its actual location, right? But it's very convenient when working with bullets and things like that. If you want to create something, you create it in your local space coordinates. So in my forward vector, which is what I usually call that, my forward vector times 100, create a bullet here traveling in the direction that I'm looking. And that's a very convenient way of working with it when you're doing coding. But then you need to project from this onto the screen, right? And so that's another project operation. Okay? And so if you have an orthographic projection, it's very easy. You don't have to have field of view and all this kind of stuff. Basically, all you have to have is a camera, and if the camera is the origin, like if the origin is just always looking this way, which is the world's simplest thing, then you don't have to worry about the camera. But normally, like, you'll be able to move the camera around, and if you move the camera left, the object appears to slide to the right. You know, and so you project from local space into world space, and you project from that into camera, whatever the camera location is. You'll see things rotate and translate around to sort of the inverse of the camera's motion, right? So if the camera moves to the right, everything seems to move to the left. If you rotate the camera up, everything seems to slide down, right? And so that's just a matrix multiply. So the camera has its transformation matrix, and you basically apply everything, you multiply everything through that, and then they will be in camera space coordinates. And then traditionally in OpenGL, screen coordinates range from -1 to +1. And so the center of the screen is the origin in OpenGL, which is kind of annoying. I don't know if we're going to do that. We're going to use normal screen coordinates, which are 0, 0 in the top left. And so basically, you just do a series of matrix operations, and then it'll say, okay, location 300, 400, -50 on the screen is 20 across, 10 down, and it is still -50 away from the camera. And if you don't want to do the camera, you can just have the origin have the camera pointing down the z vector or something like that, which is pretty much screen coordinates. And if you do an orthographic projection, there's no perspective, right? Like, it doesn't get distorted as it moves, right? You know, like if you have two things like this, you know, they'll kind of move past each other. With an orthographic projection, everything's kind of flat. So you can just do that. So I would just do for this next assignment, project from world to screen coordinates. Okay. And I want you to animate it. Animate the triangle. So have it spin, or maybe as you hit the arrow keys, it'll rotate in the direction you're talking about. Again, that it's very easy if you have the math toolbox for doing matrix math. Just every time you hit the arrow key, it moves 10 degrees in that direction. Okay. You can rotate around the X, rotate around the Y, rotate around the Z. And then finally, I would like to do lighting. Could do backface culling. So how does lighting work? Well, it's complicated. As with all things, it's complicated, but we can just make it simple, as always, to begin with. So we can just assume that, like, there's just one sun up in the sky, and it's just providing directional lighting, like maybe straight down or at an angle or whatever is going to work out for you. I don't really care. And so the amount of light you get on a triangle is the dot product. And so let's switch colors again here. It is the dot product of the normal vector and the displacement vector. To the light. So again, a displacement vector, if you've got vector A, vector B, the displacement vector is a vector, in this case it's B minus A. The vector pointing from A to B, you get that by doing a vector subtraction. And so if you have a triangle, you have a triangle, and it's got a normal vector pointing this way, and you've got the sun like over here somewhere. You take its location, your location, take a displacement vector like that, normalize it, normalize both of them, and dot product it. If they're pointing in exactly the same direction, then it's 100% lit. As the triangle rotates away, it's going to pick up less and less light until it's at 90 degrees. When the normal vector and the sun are at 90 degrees to each other, then you get no light, right? Because if there's light coming out of the screen right now, if I have my hand like this, you see how the edge here is picking up the light from the screen, but this part's shadowed, right? So add lighting, it's pretty easy. Just create a location for the sun, take a displacement vector, normalize it, dot product it with the normal vector of the triangle, and then just multiply that times the color. Just use white light. And then you'll see as you rotate it, it'll get dark and then it'll come light again. And it's a cool effect. It's a cool effect. And then after you do that, you can start adding multiple triangles and have rocket ships and things like that. Okay. All right. Yes, let me pin that on the channel here.
So eventually what we can have is basically like maybe like a camera class or something, like, because what I showed about the screen, maybe instead that could be like a camera class, and basically it has a vector 3 that is the world coordinates of the camera, and then we can create a rotator class kind of like Unreal Engine has, and that shows like the angle that the camera's actually facing. Correct? So the camera can like rotate up and down, or
the camera class is the camera class would be different from your screen class, because your screen class is literally the screen buffer. Like this pixel holds this color and this depth.
Oh, so then we can have the camera rasterized to the screen in a way, or
not unless we're going to be doing ray tracing, right? So again, the camera just transforms all the objects on the screen. So
I see.
So as I slide the camera to the right, all the objects in the screen slide to the left.
Oh, so then the camera's like the intermediary between the screen and the world, essentially.
Yes. And it's just an extra step, so I would just not do it for now.
Okay.
But if you want to be cool, you can have the triangle not move, and instead have your arrow keys, like you can do WASD and ED, and fly around the world like you're in Unreal Engine, right? So when you use W, the camera moves forward, and so when you move the camera forward, all the objects in the world move towards you, right? So if you move 1 in the X direction, everything effectively moves -1 in the X direction. And that's just an extra matrix multiply on top of what you're doing already. And so it'd be an easy.
We should just pretend like basically that the camera's looking in the positive like X direction, say, or the positive Z direction.
Just pick one.
And
yeah.
And it's at 0, 0, 0.
Yeah. That's how it would start, because then it just saves you that extra level of math, right? Always start simple and build up. So the first thing to do is to establish whatever your view matrix is, which is the direction you're looking, and then all you do is you take put your triangle in world space, like this is at location 100, 200, 300, whatever, and project from that into the screen space. And then the rest of your code will be the same. So just add that one extra step take what you have right now, which works, and have the ability to project from world space into screen space, and then it should still work.
And what about the matrix? Because programming matrices, I don't know how easy that is to do.
It's pretty easy. We went over that in IS-58A, right?
No, but like programming an actual matrix, like to do matrix multiplication stuff.
Yeah, it's easy.
All right.
All right. Quick review. So if you're going to multiply this matrix by 2, 2, 2, you turn the vector sideways, 2, 2, 2, multiply down, add across. So all these numbers are going to get multiplied by 2, so it'd be 2, 4, 6, 8, 10, 12, 14, 16, 18. So you multiply down like that, and you add across 12, 30, 48. And so this is This is vector, matrix times vector, gives you a vector. If you have matrix times matrix, you take each column one at a time and do this. So all you have to do is this. This is the only hard part. And then for a matrix times matrix, you just repeatedly do this, one on each column of the matrix, and you'll get 1, 2, 3, 4, 5, 6, 7, 8, 9 times 1, 1, 1, 0, 0, 0, 0, 0, 2. So you start off by taking this vector, turning it sideways, multiplying down, adding across, and you put the result into the first column of the answer, which in this case would be 147. 0, 1, 0, turn it sideways, multiply down, add across, we're going to get 258. And for this one, it'll be a little different because we got 2 and a 1. So we're going to multiply down, we're going to get 4, 10, 16. 4 plus 3 is 7. 10 plus 6 is 16. 16 plus 9 is 25. I think I said that wrong. It's 4, 10, 16. Okay. And then that is our final answer. Do you remember how to do that for -50A?
Yeah, I feel like doable. Okay. I'll probably have a template for the matrix that gives its dimensions, which I wondered because you said templates can't be used with a separate compilation because they don't create object files when you don't know what the type is. Like it can't create object code.
Yeah.
But what if it's just like passing in a parameter as a template? Would that be as...
Any template parameter that's not known at compile time, it's not going to generate object code. And compile time...
So as long as you have a template and then the parameter has like, I don't know, like 1 by default or something, that's fine.
Yeah, or you do what we did there and you just generate a version for 1D, 2D, 3D, and 4D. Sure.
Yeah, good
if you want. I would only do 4D though, honestly. 4D is all we care about. I mean, 2D that's a 4x4 is what we use. It's a 2D 4x4 matrix.
Okay.
All right.
Oh yeah, it could be as simple as like you have the matrix is just a vector of vectors, and then you just pass in the size to the constructor or something.
Yep. But like I said, 4x4 is the standard.
Yeah, that's what we're always going to do. Yeah,
it's standard. That's why SIMD code works on groups of 4. You know, it's very common for Neon to work on 4 integers at a time because of this. Right? 4 floats at a time.
All right.
Okay, so animate a triangle. Lighting's really easy. Just assume there's a sun up there somewhere. You can get the normal vector of a triangle by cross-producting the 2 basis vectors. That gives you a normal vector. You've already done that in your code. Normalize it. Normalize the displacement vector to the sun. And dot product them. And that's how much light you get. So if it was going to be fully red and the dot product gave you 0.5, it's now half red. And you'll see as you rotate the triangle around that the brightness will change on it. And if you want to be really cool, generate a bunch of triangles to make a sphere and rotate it, and you'll see the lighting on it. If you want to be really cool, you can do Phong shading, which will interpolate the light across corners. We're doing what's called flat shading, so the entire triangle just gets the same color. But there's Girard shading, and Phong shading, which will interpolate light across vertices and things like that. Don't worry about that. Let's do flat shading. And we can do texturizing too, but we're not going to do that today. This is the big thing. Figure out how to get projections to work. Yep. And then it works the other way as well, right? So you can click on the screen and project from screen coordinates into world coordinates and shoot a line out of the screen and see what you hit, right? But we don't have the data structure to do that right now, right? We just have a vector of triangles, right? Or a triangle, right? Right, Amelia?
Yep.
And
so then we're basically just refactoring the last assignment to work with actual 3D instead of fake 3D.
Yes. But you can make it clickable, right? So you can make it so you can click on a triangle because you've got code that should honestly be in a separate function. Like you should have a separate function saying, is this pixel within the triangle? And
yeah.
So then the user can click on it and like select the triangle, right? That's what we do. You know, if I were to click here, right, boop, that gets selected. StarCraft, you click, it shoots a ray out of the sky, out of the camera. The ray comes down, intersects the Space Marine, draws a box around it. It plays a little audio. Yes. Click on the Protoss. Yes, Executor. You know. And so that's, you can project from screen into world coordinates, and you can project from world coordinates into the screen. And it's just a matrix operation and the inverse of the matrix operation, and it works basically exactly the same way. Work. Zub. All right. See you, Amelia. Have fun. And everyone, there is going to be a not sea shanty, Irish music workshop at 4. If you guys come for that, get a extra credit point or something. So see you, Amelia. And then anyone else, you have any questions about your projects or anything like that, I'll hang out for a little bit. Otherwise, I'll start prepping for the Irish music. Okay. That's it for today. Thanks, Amelia. Good job on your project.